Mark P. Otten back with you.
Okay, so getting back to our roadmap of decision making here, when you have one independent variable with multiple levels or multiple groups that make up that independent variable, you're doing an ANOVA, but you have to make one more decision, and that is whether the samples are independent or dependent. So the previous video was an example of an independent samples ANOVA because the groups were the CSUN basketball team, the contestants on The Voice, and the CSUN psychology faculty. These three groups were unrelated to each other. They had the people didn't know each other, presumably. There was no one person from one group influencing the answer of somebody else from the other groups. So these, by definition, then were independent samples or independent groups. Now, in order to do a dependent samples example, we have to change it up. And dependent samples examples usually are in the form of one person being measured repeatedly over time. That's a repeated measures design, as they say. There are other forms of dependent samples designs that are not repeated measures. But repeated measures is the typical example. It's the most common in psychology, it seems like. And the reason it's dependent is because, let's say you're measuring me on anxiety today, tomorrow, and the next day. Well, that's me today, and then my value on anxiety tomorrow is kind of dependent on whatever I said today, right? Because I'm the same person, and so someone, let's say I'm really having a really stressed out week, hopefully not, but suppose I am. If I'm stressed out on Monday, I'm more likely to be stressed out on Tuesday, right? There's some dependence there. It's not maybe I had a really good, relaxing Tuesday morning in the office, and so then I calmed down, and then my stress was not the same. But if, let's say, I was stressed out on Monday, I'm more likely to be stressed out on Tuesday, more likely to then be stressed out on Wednesday, and so on. And so those are dependent values, right? My value on Tuesday is dependent on what I said on Monday. The other type of dependent samples example is like, let's say you're, instead of sampling three different groups that don't know each other, you're sampling some cousins, and then some brothers and some sisters or something like that. So there's three different groups, and they're all related to each other in that they know each other. They might talk about their answers or something like that. So that dependence could come also from people kind of talking or being otherwise not anonymous in the different groups. So, like I said, the repeated measures design is the most common, it seems like, in psychology research. So we're going to go with a repeated measures example here for our dependent samples ANOVA. And so suppose we sample 4 adults diagnosed as socially anxious. Now these are real studies that are done with social anxiety. You show a stimulus, let's say somebody's face in a picture, and the more you show it, the more likely that person is to become less anxious around that person or in seeing that face. So this is not a real study in that I'm using this face. There's your stimulus. Then we go a few weeks later, ask them again, rating on a scale of 1 to 7, 7 being most threatening. How threatening is the following face? There it is again. And then we wait a few weeks and ask them a third time, and there it is again. All right, so theoretically in the research, it's supposed to be a neutral face that is not smiling or frowning. I don't know if this qualifies. He kind of looks like he's smiling a little bit. Anyway, moving on. So the alternative and the hope is that, the alternative hypothesis and the hope is that someone who is socially anxious, gaining familiarity, let's say, with this face or this person over time, is going to then have a decrease, a change in their perceived threat that they see across times 1, 2, and 3. So the alternative hypothesis is that there is a change over time. The null hypothesis is that there is no change. If there's no change, then the mean in perceived threat is the same at time 1 as it is at time 2, as it is at time 3 there. The null hypothesis is that the alternative is that the null is not true. And again, you can't, in the alternative hypothesis, you cannot put like mu1 not equal to mu2 not equal to mu3. That's the wrong way to do it, because then you're implying that all three means are equal or unequal to each other when there could be a difference between times 1 and 2, but not 3 or something like that. So to simplify, we just say for the alternative hypothesis that the null is not true. Okay, so if this is the setup, then the samples are dependent. It's the same person rating the face at each time point. The statistics change, but they don't change that much. So we've done already most of the work having already completed an independent samples ANOVA. The only difference here is that we got to change the bottom part of the fraction a little bit. So I called these MS values, those are variances or mean square values. So the top part of the fraction for the test statistic actually stays the same. You calculate the mean square between groups exactly the same as you would for the independent samples ANOVA. So the only thing, like I said, is that changes is that mean square within on the bottom changes to mean square error. So what is this error? Well, it's a subset of the within. The error variance is a subset of the within group variance. So the within group variance, if you recall, was the variance of group 1 averaged together with the variances of groups 2 and 3. That was within group variance. You take the variance of group 1 independent of the other groups, then you take the variance of group 2 independent of the other groups. So it's a measure of variation within each group. Well, so you could do that again here, but then you got to subtract out variance due to the individual participants. This is the unique part of a dependent samples ANOVA. Now we have individual participants who are varying in their own way. It's like me being stressed out on Monday, then causing me to be more stressed out on Tuesday, and so on. That dependence there is like person variance for me that should be accounted for because it is me being measured repeatedly over time. Now, if it was different people at each time point, as in the independent samples case, there are different people in each groups. If that was the case, then we don't need to account for this individual participant variance because, well, the individual participants just have one score in total. So this was irrelevant for the independent samples case. Now it's relevant and necessary to account for this in the dependent samples case. So for example, with this data, the fourth person, which I haven't shown you the data yet, but I will in just a second, I promise. The fourth person varied a lot from time 1 to time 3. So there was like a really threatening rating of 7 at time 1 and then a 1 at time 2. So this person immediately became less threatened by the face at time 2, having seen it before, let's say, and then stayed at a 1 at time 3. The second person, however, 5, and then 5 again at time 2 was the rating, so sort of medium threat, and then down to 2 at time 3. There's not as much variance for that person, right? They didn't vary quite as much. So if we account for this, then that's not particularly useful by itself, right? In that we're determining that that person number 1, person number 4 varied more than the second person number 2. That's not really what we're after so much, but it's important to account for that because then we take our within groups variance, we subtract this person variance, and what we're left over with, or what is left over, is the error, what's called the error variance. The error variance is sum of squares error, followed by mean square error, which we'll see in a second. That error refers to the leftover variance after everything has been accounted for. So it's like anything else like random out there in the world that might be causing variation within our data. And that's important because on the top part of the fraction, we still have the mean square between groups. That's a measure of how far apart the means are from each other at the 3 time points. And that's going to be assessed then relative to the error variance being randomness. So that will help us answer the question, are these 3 means, time 1, time 2, time 3, different from each other relative to all of the random variation that also exists in this data set? And that's a very thorough way of asking the question, then is there a difference between times 1, 2, and 3? Can we reject our null hypothesis that times 1, 2, and 3 are different or are the same from each other? Let me say that again. Can we reject the null hypothesis that all 3 means for the 3 time points are the same as each other and conclude in support of the alternative hypothesis that they're different from each other? Okay, so all that said, what do you do with sum of squares error and then subsequently mean square error? Well, you just grab them from SPSS. So I just talked a lot about the theory of why that thing is used instead of sum of squares within and then mean square within. Well, for you guys, for your purposes, you just need to grab those values from SPSS and proceed as we did before. So I'm going to show you the numbers here again in the lecture notes. This is sum of squares between calculation. It should be exactly identical to the sum of squares between calculation that you guys made for the independent samples of ANOVA. So if you watched that video already, this will be a review of that. So here for between groups variance, we're looking at group means and subtracting again the grand mean, which is the mean of everybody. The mean of, let's say, the three means for the groups, 6.25 times 1, in this case 3 for time 2 is the mean, and 1.25 for the third group at time 3. And so the mean of those three numbers is 3.5. The other way to get that 3.5, by the way, is to just take the average of all 12 values here. So 7, 5, 6, and 7 were the time 1 values, 3, 5, 3, and 1 were the time 2 values, and 1, 2, 1, 1. So this is, again, similar to before. The only difference is that each row here represents a person. So the 7 for time 1 corresponds to the 3 for time 2. That's the same person. And so on. Okay, so you've got your group means there. 6.25 minus 3.5 is the subtraction that you make for each person at time 1. And that is the deviation from the grand mean of the group mean for time 1. So 6.25 minus 3.5, you square that deviation as you do for a variance typically, and you add them all up. So you go 6.25 minus 3.5 squared plus, and then that thing again, plus that thing again. So 4 times basically the same fraction there. You add those up, you get 30.25. Same thing for time 2. 3 is your group mean, so 3 minus 3.5 squared. And then you do that 4 times and add them up to get 1. And then 1.25 minus 3.5, that's group mean for time 3, minus grand mean squared 4 times. Added up is 20.25, and then you add up those 3 sums, 30.25, 1, and 20.25, to get your overall sum of squares between 51.5. So same process again as for independent samples ANOVA. Now before, I showed you how to get a sum of squares within groups and then a mean square within groups. Well, here I'm not showing you that because we don't need that so much. We only need the sum of squares error and then the mean square error. And how do we get those? Well, I'm going to just tell you to pull sum of squares error from SPSS and divide by degrees of freedom, which is shown here. So I'm going to show you this. We're going to back up and do the SPSS bit here in a minute as well. So I'll show you where that 9.83 came from. But meanwhile, you've got the big red arrow indicating that's from SPSS. I think I put that in there in the notes because a past student asked me, where does that number come from? I'm so confused. And I was like, just get it from SPSS. And they were like, oh, that's where it came from. So anyway, 51.5 is our sum of squares between. That's what we just calculated. That goes on the top part of the fraction. You divide by degrees of freedom between, which is the same as the previous example. Number of groups minus 1. In this case, we have 3 time points or 3 groups. So 3 minus 1. The bottom part of the fraction is that number from SPSS, 9.83 for sum of squares error. For degrees of freedom error, you do a multiplication here, and this is just a little formula to remember. For degrees of freedom error, you take n minus 1. N in this case is the number of people, and that's 4. Remember, each person is measured 3 times, so there's 4 rows in our data set to represent 4 people, 3 time points. The 3 time points is k, and so you multiply 4 minus 1, which n is 4, in this case, by k minus 1, k number of groups is 3, so that ends up being, for degrees of freedom error, in this case, 3 times 2, or 6. So, on the bottom part of that fraction, it's 9.83 over 6, gives you that 1.64. You divide your mean square between 25.75, divided by that 1.64 gives you the F test statistic 15.71. And that 15.71 is then compared to the F critical value of 5.14. This is the same critical value, incidentally, as we had before for the independent samples example. And so I will find that for you again here in a minute. We're going to reject the null hypothesis since 15.71 is greater than 5.14, and we're going to conclude with the alternative hypothesis. And what that means is that there is a significant difference across the 3 time points in threat ratings. Okay, so here's your critical value chart. Not every single example that we do will have degrees of freedom between of 2 and degrees of freedom within of 6. It just sort of happened that way this time. But the degrees of freedom within, I should say, is now degrees of freedom error. So in the case of a dependent samples ANOVA, as we are doing here, degrees of freedom 1 is degrees of freedom between. That's our value of 2 here, so you're going across the top for that one. And then you're going down the side here for the value of 6, which is what we have for degrees of freedom 2 or degrees of freedom error in this case. So going across here to 2 and down to 6, we have 5.14 again. That's our critical value. So again, based on that, we reject our null hypothesis since 15.71, our test statistic, is greater than 5.14, our critical value. Okay, so this is what our world-famous ANOVA summary table or ANOVA source table looks like. We've got a couple of extra rows in here, basically because we split the within groups variance into 3, or I guess 2, because the third column there is just the total of the other 2. So that first row is consistent with the last world-famous ANOVA source table that I showed you for independent samples examples. The between groups variance is consistent in that it's calculated the same way whether you have independent or dependent samples. So your sum of squares there, 51.5, degrees of freedom was 2, mean square 25.75, and F statistic 15.71. Now I put those values there, the mean square and the F, in bold print because we are identifying within groups error, which is the other value in bold print there. That is your mean square error. That's the one you divide by. So 25.75 gets divided by 1.64 to get that 15.71. Those other values are there, and they're important in summary form here, but they're not important to calculate the F statistic. So the other values are the within group variance for the subjects or the participants. That's that person variance. So person variance here, 0.56 ultimately. We did not calculate that, nor do we need to, but it does appear in the summary table, and we can pull that from SPSS. I'll show you the results in a minute and where we can pull that from. Same thing with the within groups total there, the 1.28 mean square, and the sum of squares 11.5, and degrees of freedom 9. Those values, again, we didn't calculate, and we didn't need to, but we can pull them from SPSS if, let's say we're writing up a report, and this world-famous source table is requested because it's world-famous, well, because it's sort of customary for psychologists to see this as a summary chart at the end of an ANOVA. So if that were requested, then we can pull these values from SPSS and report them. The totals down there, 63. 63 is actually going to be 51.5 plus 11.5. So you can skip those middle 2 rows when you're totaling that up, because the within groups total there, 11.5, is actually the total of the previous 2 rows, 1.67, 9.83. So again, 63 there is a 51.5 between plus 11.5 for within. And then the 11 for the degrees of freedom, again, is 2 for between and 9 for within, totaled up to 11. So, so that's where those numbers come from. I'm going to switch over to SPSS and show you the SPSS version of this source table. All right, so here's your data entered into SPSS. I just went ahead and entered it without showing you how I did it, trusting that you guys are skilled data entry folks now. So the main thing to note here is that the format in SPSS changes. The rule of thumb in SPSS is that if you have a person, let's say a participant in your experiment, that person deserves their own row. So in this case, we had repeated measures on the same people. So that first row is actually just 7 for that person, followed by 3 for that same person, followed by 1. And so we can just format our data like so. In the independent samples case, we had to format it differently with groups labeled as 1, 2, and 3 going down the columns. We did that because we needed to conform to this rule in SPSS that each row corresponds to one single person. And in the case of the independent samples example, we had different people in the 3 groups. So formatting it in 3 columns like this would have been would have been inappropriate in that case. So anyway, that's your rule of thumb for how to decide how to format this, or you can just notice that this video is the dependent samples ANOVA video. Notice that you're doing a dependent samples ANOVA problem in your homework and follow along accordingly. That's the other sort of mindless way to do it. So once you have your data entered, you're going to go to Analyze, General Linear Model, and Repeated Measures. Repeated Measures is code for dependent samples here. So you're going to click on that, and then you got to name your well, you don't actually have to name it. You could keep it at the default, which is factor 1, but I'm going to name it as time, and I'm going to type in 3 levels, and what that is doing is it's indicating for SPSS the name of your independent variable and how many levels or how many time points in this case there are. So we're going to call it time with 3 time points. You click Add there, otherwise it won't go forward for you, and then you click Define. And you're just going to move these 3 over in order. So if you click them in order, time 1 goes into the first slot there under within subjects variables. Time 2 goes right underneath, and time 3 goes right underneath that. So you just got to make sure that you're going in order there, and everything will be okay. So you're going to click OK. You get quite a lot of output. I think there's probably more here than you really need. I'm going to scroll down to the middle here. This is tests of within subjects effects. This is what we're interested in. A within subjects effect is a dependent samples effect, or the effect of the independent variable here. So, so this is your summary table, and actually you're just going to need 2 of the rows here. So the first row that you need is time, sphericity assumed, and the second row that you need is error time, sphericity assumed. Sphericity is a fun word to say. That is an assumption of dependent samples design that we'll talk about later. For now, we can just sort of assume that our data is ready for this ANOVA to be conducted, and I'm going to give you the green light to go ahead and interpret that sphericity assumed line. There's other fancy stuff in there like greenhouse, Geyser, and other stuff, but don't worry about those. So assuming sphericity, assuming our data is fit for this ANOVA, we have some numbers that should look familiar there. The 51.5 is your sum of squares between. Your 2 is your degrees of freedom between. 25.75 mean square between. Your F is there. And your p-value. The p-value I haven't shown you yet. That's 0.004. We already knew that we were going to reject our null hypothesis because the test statistic was greater than the critical value. So this is just confirmation of that. The p-value is less than 0.05. In fact, it's 0.004, which is quite a bit less than 0.05. So again, we know to reject our null hypothesis based on that. The error row here, that's your error sum of squares, 9.83, error degrees of freedom, 6, mean square error, 1.639. So those are the values there. So actually, in this case, your summary table in the lecture notes is actually slightly more thorough than the summary table here in the SPSS portion. Okay, so just putting the finishing touches on that ANOVA here, we're going to need to calculate our effect size, and for this one, we use a modified eta squared. It's very similar to the eta squared that we used for the independent samples ANOVA. This one is called partial eta squared. We use the term partial because we're again separating out that person variance, that variance due to the participants that is unique to a dependent samples case. So that's just built into the formula here. You guys can just use this formula to report your effect size for this particular type of ANOVA. Sum of squares between on the top and also on the bottom, and then on the bottom you just add in sum of squares error, so it's just a statement of sums of squares. So we're going to end up with 0.84 here for this example. That is, again, there's a maximum of 1 on these eta squared values, so this is a pretty high value, pretty close to 1. The larger the value, the larger the effect, but in terms of meaning, I think the meaning that comes out of this is best seen when we have multiple studies to compare. So we have a 0.84 here, but let's say we go and do this study not using Neil Patrick Harris's face, but using some other face, and then we measure the size of the effect for that one, and then maybe we see if the fade type of face matters. Stuff like that is when effect size is going to be useful the most. Okay, So the follow-up here, and we could actually have done this for the independent samples case as well if we wanted, but I chose to, I don't know, not force you to do this every single time because it would get tedious and repetitive and unnecessary. So in the case of the dependent samples ANOVA, I'm going to ask you to do some post hoc t-tests, and this can be done. Post hoc means afterwards, after the fact, and so these are t-tests done after the ANOVA, and after specifically we reject a null hypothesis for the ANOVA. So back when I had first introduced ANOVA in the last video, I talked about why we do it in the first place, and that is to kind of get this screening process out of the way so that we can run multiple tests without too much controversy. So if we were to run these, we could run these t-tests up front, just comparing time 1 to time 2 and time 2 to time 3. That's what we're going to do here, is the individual pairs of time points being compared one at a time. We could have done that at the beginning, but there was some risk with that because the more tests we do, with each one having a 5% chance of an error, we're going to run our error rate up. We're going to, the more tests we do, the more likely it is that we're going to make an error, and so we want to be conservative in that way. And so we run the ANOVA first. We determine that there is some difference somewhere between our means, and now we're authorized to follow up with the tests because it's sort of like been screened out. And so we're no longer as concerned about making an error now that we know that there is some difference somewhere. So we pair up our time points like so. In SPSS, you don't have to do this. I'll show you that it does this automatically for you. But when you're doing this out by hand, you're combining these together. So time 1, time 2 is the first combination excluding time 3. Then you go time 2, time 3. Then you go time 1, time 3. So there's 3 different combinations there. And what you do is you collapse each one down. So that time 2, time 1 test is then, it's a -4 value for participant 1. And that comes about by subtracting 3 minus 7. That's time 2 value minus time 1 value. So that second person, 5 minus 5 becomes 0. That third person, 3 minus 6 becomes -3, and so on. And that's your time 2 minus time 1 subtraction, and so on. So for time 3 minus time 2, that -2 for participant number 1 is 1 minus 3. That -3 for person number 2 is 2 minus 5. Hopefully you guys see this pattern here. Person number 3, time 3 minus time 2 is 1 minus 3, and so on for -2. So you make those subtractions, and then once we collapse down our time points like so, we can run 3 one-sample t-tests on those 3 combinations. And so this is going to be math that you've done before. This formula is the same formula that you used before. The mu value there is just going to be 0 for these comparisons because you're comparing the mean difference. The x bar there is the mean difference. You're comparing that to 0. So for example, for time 2 minus time 1, you're going to get a mean of those 4 values there that you see, -4, 0, -3, and 6. You're going to compare that value to 0, and if it's different than 0, then you can say that on average, time 2 minus time 1 is different than 0. There is a difference between time 2 and time 1. Same thing for the other combinations. The key here is to just treat each combination as its own. So the x bar, the s, that's your standard deviation. Your n, that's your n for that particular combination. Those just apply to each group individually. So again, going back to the data, time 2 minus time 1, there are only 4 values now. You just have to exclude time 3 and pretend that it never existed. So -4, 0, -3, and 6, those are your 4 values. The mean is of those 4 values, the standard deviation is of those 4 values, and the n is 4. And the same thing goes for the other combinations. So if you remember that, then you can run those t-tests, and I'll show you what it looks like in SPSS here. Run those t-tests like you did, and if you forgot about a t-test, you can refer back to when I ran you through the t-test video. And SPSS should give us the results here to compare to. And as it says here, as long as we do this, as long as we remember to do the Bonferroni correction. So I always like to put Bonferroni's picture up here because it sounds like, I don't know, the first time I saw it, I was like, did they name this after like a brand of pasta or something? And then I was like, oh no, it's actually a mathematician's name from the early 1900s who came up with this correction for doing multiple tests. So if you're doing multiple tests, as we are now, we're doing 3 t-tests, then you just have to be a little bit more cautious if you're going to reject your null hypothesis because, again, you are worried that you're doing multiple tests. So you're authorized to run multiple tests now that you've rejected your null hypothesis for the ANOVA, but statisticians are like, well, okay, you're authorized to do it, but we still need to be careful because we might, since we're running multiple tests, we might have a little bit more error, a potential for error. And so Bonferroni just said, well, take your alpha, which is 0.05 here, and divide it by 3. That's a good rule of thumb to use. And so each time you get a p-value for these t-tests, you're going to compare it now to 0.017 instead of 0.05. Okay, so we're back to our data now to run these 3 follow-up or post-hoc t-tests to follow up our ANOVA. So we rejected the null hypothesis. We're authorized to do this so long as we use the Bonferroni correction. So I'm going to run all 3 at the same time. We're going to go to Analyze, Compare Means, and Paired Samples t-test. This is a shortcut. You could run one sample t-test, but if you did that, you'd have to reorganize the data like you saw in the notes there by doing some subtracting. So here SPSS will, if you go to Paired Samples t-test, will do that subtracting for you if you move over the variables in order appropriately. So we're going to go variable 1 time 1, variable 2 time 2, then we're going to go variable 1 time 1, variable 2 time 3. You just got to make sure you get all possible combinations here. The last one here is time 2 and time 3. So it should look something like this, where that pair 1 is time 1 time 2, pair 2 is time 1 time 3, and pair 3 is time 2 time 3. You can actually flip the order around if you want, but as long as you have all 3 combinations in there, you'll be okay. So you're going to click OK once you have them moved over, and you're going to look at your output here. So this output, you're going to look at the bottom box. The first box there gives you some means and some standard deviations of each particular time point. But we already found some of those statistics by hand. If you've done this, well, not by hand. Well, maybe you did do it by hand and you're really heroic, but you probably were calculating those in Excel. And so this is a way, this first box here is a way to double check your work. But I will let you do that, trusting now that you have some experience with Excel. So the box that we really want to look at here is down here at the bottom. This is these are your 3 t-tests, and so you're going to get 3 p-values here on the outside. And so let's start with that. The first one, time 1 minus time 2, the p-value is 0.080, greater than, not 0.05 now, 0.017, because we're doing 3 tests, 0.05 divided by 3. Either way, 0.08 is greater. And so we're not rejecting that null hypothesis. However, for time 1 minus time 3, we have a 0.006 p-value, so we are rejecting that null hypothesis. And what that tells us is there is a significant difference between times 1 and 3, when there wasn't a significant difference between times 1 and 2. And then here at the bottom as well, there is not a significant difference between times 2 and 3. So that's pretty cool in the sense that we have a little bit more detail to add to our conclusion, right? With the ANOVA, we said that there's a significant difference between the 3 time points, but we didn't know which time points were different than which other time points. Now we can say not only is there a difference, but that difference is between times 1 and 3. And so time 2 is just kind of like getting in the way. So that's kind of a cool detailed result that we can get as a follow-up to the ANOVA. Some of the other statistics are here as well. You can look for each t-test here. You've got the t-test statistic in the t column. So for that time 1, time 2 comparison, it was 2.6. For the time 1, time 3 comparison, 7.07. And for the time 2, time 3 comparison, 2.78. Again, that's the t-test statistic for each test, which you can get by that formula in the lecture notes and by way of Excel. And then for degrees of freedom, each time it's going to be n minus 1, and n is 4, so it's going to be 3 each time. for each test. Okay, so I skipped the Excel for this particular example, but I'm hoping that you guys have some experience and some detailed lecture notes to go off of. So as always, come to my office hours, talk to me during the computer labs, make an appointment with me in my office that is not during my office hours. All of those things are available to you to get you straightened out on all this ANOVA and follow-up t-test stuff. But hopefully it was also kind of fun. Well, maybe not. All right, we'll see you in the next video.